Good afternoon, and thank you for that introduction. So some of you might recognize the image of the Perseverance rover. It's looking at ingenuity, sort of me and my team's way of wishing the helicopter well before its first flight on Mars. These two robots have really helped us make some enormous strides in autonomous capability. And today I'm going to share with you how this was possible. Next. So NASA's mission is to explore, discover, and expand knowledge for the benefit of humanity. And next, some of the ways that we've been doing this is through sustained robotic exploration. This timeline here shows the timeline for Mars, which is an area that I've spent a lot of time working in. So the very first robot we landed on Mars was Viking, all the way back in 1975. And once we were in situ, on the surface of Mars, it really was clear that the amount of knowledge we could get was not at all comparable with what we could get from orbit. And it really started this era of robotic exploration. Well, it wasn't easy. We had a number of attempts. Not all of them succeeded. And then in 1996, the Pathfinder mission landed on Mars. And it carried with it a little robot. It was a technology demonstration, the Sojourner rover. And it pretty much stole the show, because now you weren't stuck at any one location, but you could look just beyond the horizon and see an interesting target and actually drive up to it and observe it. And with all the success that that had, we really wanted to now put a scientific payload and put a robot that was the actual real mission that had wheels on it. And that was the Mars Pathfinder mission with the Sojourner robot, with actually the Spirit and Opportunity robots. I was actually in college, and they were supposed to last 90 days. And I never thought that I would actually graduate, work for years on the mission, and move on to the next mission, and they would still be exploring Mars. Opportunity lasted for 15 years. And that really, with the Mars exploration mission, is the start of what we think of as the modern era of robotic space exploration. And since 2003, with overlapping missions, we've had a continuous presence on Mars. This has really helped us make a lot of advances because we now have a lot of data. So next. We've utilized robots of different types. So on the top left, you're seeing Sojourner, which is a little microwave-sized robot. All the way to the top right is Perseverance, which is the size of a little car. And the mast is 7 feet tall, so it's actually a lot taller than I am. And starting to characterize what are the sorts of robotic capabilities that have the most value for space exploration. Next. And I'm summarizing here the 4 main categories in which these fall. The first one, as I was mentioning before, is mobility, getting from place to place when you have a diverse planetary surface allows you to study in one location, move to another location of scientific interest, and get a lot of data with a single mission. And once you've observed remotely through imagers and other sensing, we really want to use a robotic arm to be able to touch the surface. And we carry a suite of instruments. In the inset on the top right is the turret at the end of Perseverance's arm. It has on it a drill, so you can drill into the surface. And it also carries a sort of instruments such as Pixel and Sherlock, where we can put them within millimeters of the surface and get really detailed information about the mineralogy and the chemistry of Mars. But a lot of the planetary surfaces are really harsh environments, and what you see on the surface is very exposed, and if you're going to find signs of life, it is very likely subsurface. So sampling has been a major aspect of the missions where we are looking for life. And on Perseverance, we have a robotic drill that we can drill into the surface and collect intact cores. And on the picture where I show sampling, you see the external robotic arm docked with the rover's body, where it's transferring that sample into a second robotic arm, which is inside the rover, which performs a lot of characterization. And then if you play the animation, most recently with Ingenuity, we've had aerial mobility. And this is allowing us to get to places that we just couldn't with a roving mission that is restricted to the surface. And next. So with Perseverance and Ingenuity, they've really exceeded our expectations in terms of what's possible on Mars. Even though we've been on Mars for such a long time, the enhancement that we got has been quite significant. So Perseverance has collected, to this point, 23 sample cores. And not only is this at twice the rate that we collected samples from any prior mission, but they're also much further apart. And a lot of the reason we can collect samples from a diverse set of locations is because of the autonomous navigation capability. So 88% of all of the driving has been autonomous. And what's really been exciting to us is that we've driven 20 kilometers and we've broken a lot of records. And it's not just a one-off. So I'm showing here the longest drive we've done on Mars is 348 meters. Before Perseverance landed, the record for the longest single sol drive, and a sol is a Martian day, which is just a little bit longer than an Earth day, was with the Opportunity rover. Almost 19 years that record held. And many of you who work in robotics will appreciate, we really put everything together and worked really hard to get things just right. And so that we could exceed this record and meet that record. And we did, sort of, the cosmos had to come together to do it. But Opportunity never did it again. And with Curiosity, it wasn't even able to meet that record. What's been really amazing with Perseverance is that we are consistently now able to do these hundreds of meters drives pretty regularly. It's exceeded that record 23 times, and it's pretty commonplace to drive in that manner. And we now drive over multiple days. So we come in on a Friday, and we'll tell the robot to drive. It has a limited amount of power per day. And then you come on a Monday, and it may have driven 700 meters and is in an entirely new location. And not only is it in a new location, it's also taken an image, determined what the most interesting scientific target is, observed it, and sent the data back to us so that we now have this available to us to determine whether we want to stay or go to the next site. And then lastly, the helicopter, it was supposed to just show us that it was possible to fly on Mars. And we've now had 52 flights. So this has really sort of changed the capability where we now are starting to look at missions where aerial mobility as an integral part of what we do. We've flown 12 kilometers and had an hour and a half of autonomous flight on Mars. Next. So one of the things that's different between space robotics and terrestrial robotics is just the time delays and latencies. So Mars is really far away, and it takes a one-way light signal from Earth, can take up to 24 minutes to get to Mars. And when we collect a ton of data, it's not efficient for the rover to directly send it to Earth, so we actually transmit it to orbiters around Mars and then send it down. This really makes it really amenable for autonomous capability. So next slide. I'm going to go over some of the autonomous robotics capability that is a necessity. In the case of autonomous planetary exploration, you need this capability in order to accomplish the mission. So it's really a good opportunity for a lot of technology deployment. So in the next slide, this is an image of Jezero crater. When we were planning the next mission to Mars, we were looking for signs of ancient life, and Jezero is a crater in which there's a delta, and it's an ancient liver delta, and the probability that we would find signs of life was really high. But the crater walls and the walls of the delta are tens of meters high, and if we landed on the edge of one of those, it would sort of be detrimental to the mission. So in the next slide, we have autonomous technology where as we were entering the Martian surface, and this is data from that landing, we're tracking using computer vision techniques the features to detect where we were headed. And we had the capability that if we were headed to a hazard, it could divert us away from it. So we knew that we could target a place like Jezero because we were going to avoid the hazard. And as you'll see as it converges, actually click the slide so it'll play the animation. It converges on a solution. We were headed to a hazard. And it did a divert, and the rover was safe and landed in a safe area, but it was all the way on the other side from the delta than this hazard. And on the next slide, you'll see where we actually ended up. And that there is the landing location. And now we did some science there where you're seeing the different image colors show the different observations we did. But then there was nothing very interesting, and we needed to go make it all the way to the delta. And this is where we really used autonomous navigation, because it was taken a prior mission almost a year to get there, whereas Perseverance was able to do that in the order of weeks. And once we got to the delta, there we accomplished some more rich science. And on the next slide, I show on the x-axis, you're seeing the sols on Mars, and on the y, you're seeing the distance driven. And the different colors are the different modes we have for autonomous driving. And the orange is where we turn on slip detection, autonomous navigation. And as you'll see, most of the mission has been autonomous. And the column in the middle shows when we did the drive from where we landed to the delta, and there was mostly a significant amount of just driving autonomously. And on the next slide, I show a comparison of all of the missions that have had autonomous capability on Mars. And if you look at the top row, you'll see that Perseverance is significantly more autonomous driving than any other mission. We've driven almost 1,300 meters autonomously, whereas previously it was Opportunity, which had driven 2.4 kilometers in its 15 years. So this is a significant leap in capability that we've been able to achieve. And so some of what I was going to go into next is there's a lot of things that we could enhance and improve, but we need to reliably function in an area where no human can go intervene, and we need it to work. So there were some choices we made that allowed us to do this. If you go to the next slide, one of the obvious ones to most of you will be the computing. So computing just has an outsized impact on autonomous capability. We looked at data from our prior missions, and we look at the logs, and you look at the CPU utilization, and we were just railing and utilizing all of the computing. But less than half of the processing was available to the robotics, because the robot needs to do health and safety, it needs to survive, it needs to do a lot of things. And one of the easier ways to solve this problem, because we need to use radiation-hardened processors, so the processor we use is a RAD 750, it's just a 133 megahertz processor, is we just added a second one. So we added a second processor, and the purpose of that processor is entirely to just do navigation. And the other data showed us that most of the computing we were spending was on the computer vision. And so we did dedicated hardware to do FPGA-based computer vision, which also really sped things up. And then we updated our cameras because the sensing is very important. And then in other ways, we made advancements in our hardware because the wheels on Curiosity were starting to tear. But what was causing them to tear was these tiny little rocks. They're not actually hazards for autonomous driving, but they're really sharp and they were volcanic. And we could not use autonomous driving because it wasn't a hazard to the autonomous capability. So instead of solving that issue and trying to classify which tiny pebbles are hazards, we just made the wheels a lot more robust to that kind of problem. If you go to the next slide, here we also made the obvious changes, which is to the algorithms so that we would have improved capability for navigation. And a lot of this is in the area of just slip detection and being able to predict, because your wheels are turning and you're going to get some sensing information, but you need to make a prediction about where you'll be as you're thinking and processing to execute that. Then there's some really practical constraints, and this is an example of if you have a robotic system, unless you solve the problems that constrain you the most, you're still not going to be able to use the autonomous capability. And in our case, we need to talk to Earth, because if the robot can't communicate with Earth, it doesn't actually matter, it's not going to survive very long. We used to drive autonomously, and as it's getting around hazards, it might end up in an orientation where part of its body or some terrain occlusion is occluding its view of Earth. And we wouldn't use autonomous driving in complex terrain. And so in Perseverance, we added the capability where, as it's driving, it knows where Earth is, and if it is run out of time and it can't turn to Earth, it stops a bit early, and then it'll continue to navigate till it finds a spot where it can actually do the turn to find Earth. And the other one is things that are, for planetary exploration is we don't have GPS, but your attitude is really important, not just so you can find Earth, but you want to prevent drift so you can navigate. And for that reason, it autonomously knows when it's drifted too much, it'll find the sun, it uses the sun to fix its attitude, and then it'll continue driving. And then there are some other cases, as I show on the next slide, where you don't really want to wait till the technology is good enough or complicate the system. And in our case, it is sand. So a lot of our previous rovers have gotten embedded, which really slows down the driving. And we could either try to reliably detect sand with cameras, which don't actually do stereo very well on sand, or we chose a simplified approach. And here I'm showing a picture of the tools we actually use to drive the robots, where even with low latency, humans can tell it. These are the patches on the map where there's sand, and it tracks its uncertainty on board and is able to avoid them. So really, we just creatively simplified the problem and utilized humans so that we could continue to actually deploy a system that was robust. If you move to the next slide, these are images taken from the navigation cameras. And because the color doesn't really add value to the navigation, you're seeing these images. This is what we use for driving autonomously. And this is an actual drive from Mars where it's driving through the terrain autonomously navigating. And then on the next slide, you're going to see that we've climbed onto the crater, and these are tracks as it climbed onto the crater, an autonomous drive that it did, navigating through hazards to climb up onto the delta and continue exploring. But as we start to cover these really long distances, what happens is you can miss things along the way. And what if you're driving, and you're driving hundreds of meters, and there's a really interesting target? So another capability we have, which I'll show on the next slide, is autonomous science. And the next slide shows you can see a terrain, and it sort of looks really benign and potentially not very interesting. We take a wide field of view image, and the robot picks like 250 features in it, and it'll use algorithms to detect what is the most interesting for science, and then use a narrow field of view imager, and you'll see on the next slide, we can shoot a laser on it, and it creates a plasma, and we study that with a telescopic imager. And this is the image from the target you saw on the previous slide, where it picked the most interesting target. And it's returning the mineralogy autonomously. And so we're now, as we're driving, we don't miss interesting science. We don't have to stop just for the science. So I'm going to show you where we are, sort of close to where we are. We've driven further than this by now. Is the helicopter is now able to fly over hazardous terrain. And so it's really allowing us to cover areas that we couldn't otherwise. And on the next slide, we've now collected, these images are taken by Perseverance, where it's holding the sample core up to its imager and looking at the cross-section. A diversity of samples, and we're now ready to bring these back to Earth. And I'll end with a video which shows you sort of the mission that's going to bring them back. And if you play the next video, so it's Perseverance. I think you might have to click one more time. Actually, it's starting. So this is Perseverance is collecting these samples. And as it collects the samples, it's getting ready for the next mission that is going to land on Mars, which is a lander. And here you see Perseverance watching the lander coming onto Mars. And this is going to happen in the 2030 timeframe. And it drives up to the lander. And there's a 7 degree of freedom robotic arm on the lander that takes the samples that Perseverance has and transfers them into this canister. And one by one, we collect the samples in it. And then we close the canister. And we launch a rocket from Mars that is going to be carrying this canister. And it launches into Mars orbit. And it's going to release the canister into Mars orbit, where another orbiter from the European Space Agency, the Earth Return Orbiter, is going to rendezvous with it. It has a robotic arm that's going to capture this canister. And then ERO is going to close its lid and make its journey back to Earth and deliver these samples, eject them into the Earth's atmosphere, where we're now going to have them available to study in laboratories all around the world. And a mission like this is really possible. And I have the last slide. The mission like this is really possible because of global collaboration, but also the autonomous capabilities that we are further advancing in order to make it possible. It's a mission entirely driven by robots, and we really need all of this capability to work robustly. So taking the latest innovations in AI and technology and deploying them in the robotics scenario is what we're sort of hoping to do. So thank you.